Good morning. Now, in today's class, we will learn about direct form and structure of IIR systems and cascade form realization of IIR systems. So, these are actually the basic topics. That is, IIR systems, that is infinite impulse response. Such filters, they can have various types of structures. One is direct form 1 structure, the other one is direct form 2 structure, and the third one is cascade form structure. So today we will brief about direct form 1 structure, direct form 2 structure, and finally cascade structure. So before going into the details of the structures, finally let us get familiarized with some of the symbols that may be used in the following sessions. Okay, now see the first one, it is adder. This is actually how you represent the addition of two discrete sequences, say x of n and y of n. Here you can see x of n and y of n, and on adding you will get the output y of w of n as x of n plus y of n. See how it is represented. The addition symbol is there. So adder is a symbol that is just used for the purpose of addition. Now let us see multiplier. You have a discrete sequence x of n. You are multiplying it with a constant, say a, and the output will be a into x of n. Okay, so this is the representation for a multiplier. Now that is multiplying with a constant. No, you are not multiplying two sequences. Instead you are multiplying a sequence with a constant. If that is your purpose, then you can use this particular symbol. Then if you have got two sequences, say x of n and y of n, then you are multiplying those two sequences. Then you can use, say, modulator. This is how a modulator is represented. See, into sign. The output will be x of n into y of n. Now suppose that you have got a sequence, say x of n, and you want to delay it uh, 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 by 1 unit, then you use this symbol z raised to minus 1. So when it goes through this, it will become x of n minus 1 because it is representing delay. Now just the reverse, if you want to increase it by a step 1, or if you want to advance it by one step, then you will have to pass it through z. So it will become x of n plus 1, not n minus 1, it will be n plus 1. Okay, so when you see such representations, you must understand that this is a, if it is z raised to minus 1, then it is a delay operation. If it is just z, it is advance operation. So just get familiar with all the symbols. Now based on the symbols, suppose that you have given an equation like this. How will you draw a corresponding figure that represent this particular sequence? Xn is the input, yn is the output. Okay, now in the output, what all things you need? First of all, you see here x of n. It is delayed by z raised to minus 1. It is the delay operation. Okay, so x of n, the output, it is delayed by z minus, so the output of this will be x of n minus 1. Then it is passing through this. What is this? This is a multiplier. So x of n minus 1 is then multiplied with a constant, say p1. So so that particular term will be p1 into x of n minus 1. See, so this term we obtain. Now the other one, here you have got a y of n, that is delayed by z raised to minus 1. So that will be y of n minus 1. Again it is multiplier is there. It is multiplied with a constant, say minus of d1. So this output of this one will be y of n minus 1 into minus d1. This one. Okay, now after that there is one more case. See, x of n, it is straight away going to a multiplier, and it is multiplied with a constant, say p0. So the output of this will be p0 into x of n, this one. Now all these terms are finally added. So this is the addition operation. See, this is how you obtain a particular equation, or if you are given an equation like this, this is how you represent it using the basic building blocks. Okay, that is just for your information. So when you see such figures, we will be able to analyze what all these things are. What is z raised to minus 1? What is this symbol and all? Okay. Now we are going to study about the basic structures of IIR systems. Now The system function or the transfer function of an IR filter is represented by this equation. This one is a numerator, this is a denominator. Hs is a system function or transfer function, and now this equation is of the order n minus 1, and this is a corresponding difference equation. Okay, so if you have an IAR filter or IR system, the system function is given by this equation and the corresponding difference equation is this one. Okay, now we will learn in detail about all various types of structures, say direct form, one structure of IR systems. Okay, now the transfer function h of z of IAR system is divided into two parts. Okay, and they are connected in cascade, and the first part is named by the name h1z, and that h1z will contain only zeros, and the second part is called by the name h2z, and it will contain only poles. So see here, this is how the transfer function or system function of a direct form one structure is represented. It is divided into two parts, that is h1z and h2z. Here h1z contain only zeros and h2z will contain only poles. Now here what is h1z and what is h2z? Here h1z is this one. Okay, that is the numerator part that I have already shown in the above slide, and h2z is the denominator part of the equation that I have shown in the above slide. Now the equation, this h1z and h2z, they can again be rewritten in a particular form, that is h1z can also be written as w of z by x of z. And it is already, this one is given, so it is there, but it can also be represented like this, and in time domain it is expanded like this. Okay, whereas h2z, which is already mentioned here, the same equation is written here also, see this one, but it is represented as y of z by w of z, and in here also it can be represented in the time domain as this. So h1z and h2z are given separately, and their time domain representations are also given. Now this is how the direct form one structure is represented. See how it is represented. This is the, it has got two structures just in the form of a ladder. This one has got, this is actually the h1z part, it will have only zeros as already said. This is the h2z part, this is its representation, and it will contain only poles. Now these two are connected in cascade to form direct form one structure. Now it has got m plus 1, m plus n memory units, m plus n plus 1 multipliers, and m plus n adders. So that is enough from direct form one structure. Just study how to draw this structure. Okay, now so this is enough for direct form one structure, that is you have to represent how it what is the system function of direct form one structure, that is it has got two parts, h1z, h2z. What is h1z and what is h2z, its representations, and finally its pictorial representation. Always mention that h1z will contain only zeros and h2z will contain all poles. When these h1z and h2z are cascaded, we will get direct form one structure. Now similarly you can explain direct form 2 structure. Here there is this particular system has no order. Order is not important, so we can interchange this h2z and h1z in any way that we can. Okay, in this direct form 2 structure, h1z is represented like this. See here it is the other direct form one's numerator, and direct form one structure's denominator is becoming here as the numerator. It is represented as Vz by Xz. In the earlier case, that is in direct form one structure, this was actually the H2Z part. Now here it is the H1Z part. That is, we can the order can be interchanged. There is no problem. Why? In direct form 2 structure, there is no importance to the order, and it is the time domain representation. Similarly, H2Z is represented like this, but whereas in direct form one structure, this was actually H1Z, right? Again the time domain representation. Now this is a pictorial representation of direct form 2 structure. Here there is a delay elements and all are there. Why we say delay elements? All here there is z raised to minus 1, so some delay elements are there, and okay, Here also there are m plus n plus 1 multipliers, m plus n additions, etc., and set of mn delays. Now here the structure actually minimizes the number of delays, and so it is also called by the name canonic. This is the most simple representation of direct form 1 and direct form 2 IAR filter structures. You can just go through it. Okay. Now the last one is the cascade form structure, and the cascade form structure, again it is represented by the same equation, whereas here the system is factored into a cascade of second order subsystems, such that in this case HZ is represented like this. It is divided into a lot of subsystems or small units. That is why it is represented by h of I z, where I can be 1 to infinity. Now if that n is odd, one of the subsystems will be of first order. See, these are all subsystems: subsystem 1, subsystem 2, subsystem 3. All these are connected in series to form the cascade structure. Okay, now this is actually the most general representation of this subsystem h of I z. So h of I z is nothing but the system function of the subsystem, and it is the general representation of a subsystem is like this: h of I z equal to this one. Okay. Now each of the second order subsystems, they can be, each of the subsystems can take the form of either direct form 1 structure or direct form 2 structure. It actually depends. So since there are many ways of pairing poles and zeros, a variety of cascade representations is possible. So that's all for today. So here what you have to learn is about the system functions of direct form 1 structure and its pictorial representation, and again the system functions of direct form 2 structure and its pictorial representation, and finally the system function of cascade structure and its representations. So here I think there is all equations are similar, but the numerator and denominator alone will be interchanging in when you are taking the case of direct form 1 and direct form 2 structure. So nothing more to learn. So when you just only a few equations are there for you to learn here. The other one is just interchanging. Okay, so for today this is enough, and please go through all this. Okay, thank you.